Hello, now started to introduce my work. And first, I would like to consider the structure of kernel distributions. And the kernel distribution is that, for example, previously we call the Hodges-Lehmann estimator. It is the kernel is indeed the Hodges-Lehmann kernel. For example, maybe if you say H is equal to just the sample 1 over n, 1 over k, plus 1, 2, 3, the sample S1 plus S1 plus S2 plus Sk, right? And then for the Hodges Bickel-Lehmann spread, the kernel is, for example, for the standard deviation, the kernel is indeed the 1 over 2 x1 minus x2, right? So this we can call it kernel distribution, or if in Bickel-Lehmann's words, it is called pseudo-sample distribution, or because the concept of U statistics was first from Fisher and Hamels, and Servering he pointed out this trimmed U statistics, and indeed he is the first considering the structure of U statistics. It is in their words. So generally, the structure of U statistics, kernel distributions, or pseudo samples, and they are referring to the same things. And Hodges and Lehmann are, to my knowledge, the pioneering who really first considered such kernel distributions. And indeed, they in their landmark paper, although this paper is very less unknown until now, it just have 22 citations. But in their paper, this landmark paper, they first consider this theorem called, if you consider a sequence of real numbers satisfying this relation is indeed a unimodal relation, because if you consider the probability density function first from 0, and then larger and larger until to am, and then it becomes smaller and smaller to 0. So this is a unimodal sequence. For such a unimodal sequence, if you're defining a sum as SKS, as the pair product, sum of the pair product, and then it can be shown that if this pair is very close, and then it will be always greater than those pairs relatively far away. And this conceptually is not very difficult. For example, if you consider this pair, we slice, this is, for example, this is A1 and A2, we slice a very small pair, and then we slice all these pairs, slice another slice, here is another slice, we slice all these pairs, and then sum it. This probability density, of course, will be very high, because it consider all. It is just like a cumulative distribution, nearly exhausts it all. But if we consider relatively far, for example, maybe if it is S2, S3, then it is A5. It is not A2, but A5 or A9, and then it is very far away. And then when it is very, very far away, for example, just two. And then in this case, we just consider 3 points. 1, 2, 3. So just 3 points. If you're adding together this numerically, this value would be, of course, much smaller than a lot of probability density product, and adding together, it would, of course, be much smaller. So conceptually, this is not very difficult to understand. And this already determines that if we consider a pairwise differences distribution, because in our definition, the pairwise differences is the small value minus the large value. So in this case, it should be a monotonic increasing distribution. If it is the greater value minus the smaller value, then it should be a monotonic decreasing function. And they show that yes, and they also show that it is because they do not distinguish, because the pairwise differences need to hold the case that the first choice should be smaller than the second choice, and they don't consider this case, so they show that it is unimodal and symmetric about 0. But if you just consider the pair, only the pair that is smaller, the first is smaller than the second, and then it will be a monotonic distribution. And since it is a monotonic distribution, monotonic increasing distribution, if we square it, and then it will become a monotonic decreasing distribution, as shown here. And then if you multiply all values with half, it will not change the monotonicity, and the mode is 0. Yes, right. The mode is 0. And then so that means the standard deviation kernel distribution using this kernel, it is a monotonic decreasing distribution, and as we showed previously, a monotonic decreasing distribution is always second gamma ordered. Therefore, we can say that the standard deviation kernel distribution is always second gamma ordered. So it holds it. So then we can hold a very nice structure, and this basically can be extended to the kernel distribution of other Bickel-Lehmann spread, right? For example, the pairwise differences. Yes, it's basically the same, and then we can try to define extend it, because the standard deviation is the square root of the second central moment. And if we extend it to the third and fourth, it is possible, because in 1997, Hefner, he obtained an unbiased estimator of the K central moment using U statistics, and he showed that the kernel function is dist, a very complex. This is a relatively complex function, but however, a little bit surprisingly, I show that we can't this even such a very complex kernel function. The result kernel distribution still have some very nice structures, and I show in theorem 2 that we first consider a set of T comprising all pairs. Because, for example, I would like to give you an example. Wait a minute. Yes, I would like to give you an example. 1, 3, 5, 8, 10, or just 1, 3, 5, 8. And then first, all pairs, all possible pairs. For example, if you consider just 3, so it is the first pair is 1, 3, 5, and then 1, 3, 8, 3, 5, 8, and then this is the, or we can, no, 1, 3, 5, 7, 9. Yes, okay, 1, 3, 5, 7, 1, 3, 9. And then it is another possible is if the k is equal to just, we can just consider the second central moment. Okay, 7, 3, 5, 9. Okay, 5, 7, 9. And then and all these pairs. The first it is the 5v, and it is we took the computing plugging this kernel plugging these pairs into the kernel function. And then there is a result. This result is not as simple as the pairwise differences, so I do not compute it, but there is a result. So, for example, I can call it S1 or X2 or X3. Okay, X3. And anyway, there is a result. So this result is the pair, the first element in the pair. The second is that the corresponding probability density of this pair, and this is from this probability density is from can be computed using the k times the probability density of each element. For example, for the first element, there is normally there is a Fourier distribution. So this is a Fourier distribution because for example, for this such a distribution, we every point, for example, 1 is from this point, and maybe the corresponding probability density is 0.1. And then for the 5, the corresponding probability is 0.2, and then we just time it. Yes, just time it, and then or even for the 5, maybe 0. Also 0.1. Okay, and then time it, and then it is 3 times. Okay, 3 factor. Okay, and then this is the probability density of this pair. Yes, of this tuple. So if we're defining a set T comprising all pairs like that, and then we're defining another subset, a subset of T, such that we consider all the pairs, all these tuples, tuples satisfying that the first quantile minus the second quantile, or the first quantile minus the last quantile is equal to a delta, equal to the same value. For example, here we can find that the first quantile minus 5 is equal to 4, and then it's equal to 6, 8. Yes, 4, 6, 4. Okay, and that means if we consider a subset, for example, this is the T, a subset of T delta, it will be equal to 1, 3, 5, 3, 5, 7, 5, 7, 9. Yes, this is the subset of T, and another subset can be 6, right? So this will become a, and then we can define a component quasi-distribution. We consider the distribution of this subset. This component quasi-distribution has a quasi-probability density function that we sum over all the probability density such that the pair is in the set, in this set, and also the first element. This, if we're returning, for example, the x1 is equal to the same value. So it is like that, for example. So and then in this way we can decompose it, the central moment kernel distribution, as a quasi-mixture distribution comprising an infinite component quasi-distributions, and each corresponding to a different value of delta, and ranges from Q, because the delta is a monotonic. You remember that the delta is indeed just the pairwise differences, right? So it is a monotonic increasing distribution from the quantile 0 minus the last quantile 1, so it is a negative value, and to 0. And each component quasi-distribution has a support of this. So it seems complex, but intuitively it is not pretty difficult to understand, because for example, here is the sample. I assume this is the sample. This is the whole population of the central kernel distribution. This is the central. The green one is the central kernel distribution, and then a quasi-mixture distribution, a component quasi-distribution can be seen as that. For example, I set the I said the red one. The red one is a component quasi-distribution, because the component quasi-distribution is related to a value of delta. So this delta is from here to here. It is very close to the range of this central moment kernel distribution. But if we consider smaller delta, right, and then this component quasi-distribution have a smaller delta. If we even consider even more smaller delta, yes, and we can consider even smaller delta. So anyway, that you can imagine that you can imagine that we decompose the central moment kernel distribution as many component quasi-distributions. So it is called quasi because the integer is not equal to 1. The whole of the central kernel distribution is the integer is 1, but we decompose it into many, just like a mixture distribution. We decompose it into many component quasi-distribution with smaller and smaller ranges, right? And here is so it's just like that for smaller and smaller ranges. And the number is not infinite, and smaller ranges. And more importantly, you can imagine that because for example, if the range is close to 0, and then according to remember that according to the previously we just proved that the monotonic the pairwise differences is this is a monotonic increasing distribution with mode at 0. So if this range, the component quasi distribution, if the range is close to 0, and then you can say that this you can imagine that this relative differences will have a very high probability density. So basically, no matter which kernel, although this component quasi distribution has its own structure, it might have a very complex structure. For example, this if you consider the component quasi, the range is very large. It might not even be unimodal. It might from here to here, right? It might be multimodal. It is I don't know. I don't know any structures about the component quasi distribution. But even we don't know that, since we can decompose it to many component quasi distribution, but we know generally each component quasi distribution, if the range is very small, then it should have a very high probability density because the pairwise differences is a monotonic increasing distribution. So that means the central moment kernel distribution, it is generally, if you're assuming the component quasi distribution is uniform, if you're ignoring the shape of the component quasi distribution, and then it should be first, if it is from the start to general increasing, and then it should start it decreasing, because we should fit the trend of the monotonic increasing distribution. So this theorem, this is a very and then indeed we prove that each component quasi distribution has a support and this support is directly related to this these differences. So that means if the component quasi distribution with a very small pairwise differences, the support will be very small, right? It generally guarantees that. So this theorem the proving of this support is very complex. You need to decompose it, this very complex function, and then find an equivalent. But generally, this component quasi distribution, it guarantees that, because if we summing all this component quasi distribution, and then it will equal to the pairwise differences distribution, and so the shape of this of the pairwise difference distribution will guide the distribution of the central moment kernel distribution, and make it be a monotonic increasing. It is monotonic increasing when the value is smaller than 0, and become monotonic decreasing when the value is greater than 0. And indeed, the medium is also it will also exhibit very close to 0, because for example, you consider the because it can cast it as a weighted mean of the medium of each component quasi distribution, and you can imagine that when the pairwise difference, when this difference is very small, and then the medium will just close to 0, right? Because when it is very small, it is just when it's 0, it is just 0. So the medium is 0, and it's 0 when it is 0. When the component quasi distribution is 0, and this medium assigning a very high weight because the corresponding probability density is very high. But however, when the pairwise differences is very large, the mediums is of course it might be very far away, because if the school it might be far away from, for example, if for this large quasi distribution, the medium might be even here, right? But this is not important because it's this is very large, so it's assigning a much smaller weight. So it assigns a very small weight. So that means this medium, you can just imagine that if we consider the weight of the medium, it should be just like this. Close to 0, we'll assign a very high weight, and then far away from 0, we'll assign a very small weight. So the medium should be around here. It is a very close to 0, And indeed, we show some examples in no matter, for example, the Weibull, Gamma, log normal, and Pareto, and they are all very close to zero, and smaller or equal to 0.1 sigma for the third and fourth central moment kernel distribution. And if we are assuming the medium central moment is equal to 0, and then for an even kernel ordinal central moment kernel distribution, the average probability density on the left side of 0 is much greater than the right side because of, if we arrange it, this is because the support interval determines that for an odd, if you consider it k is equal to even, and then the left hand side is much smaller than the right hand side, so it will become a skewed case. It is, here is a symmetric. This is just for odd, but if for even, it is a highly, just like this. Yes, just like this. It is a highly skewed case, just like this. Yes, just like this. The mean is here, which means because the support interval determines that. So therefore, because it is a skew, but however, medium is around 0. So that means the right hand side must have a higher probability density within a very small, such a small range, in such a small range. So it must have a higher probability density than the right hand side, right? Than the right hand side. And for the odd ordinal distribution, this is relatively challenging. And if we consider the original distribution is right skewed, and then this component quasi distribution will become left skewed due to if we are arranging this, finding the derivative of this kernel function. And then we can say that the probability density of the right hand side of 0 will be greater than the left side. So it will become a just the opposite. It's not like this right skewed. It is a relatively left skewed. Yes, but generally on average, the overall, because the monotonic decreasing of the negative pairwise difference distribution, and it guided the shape of this case central moment distribution. And therefore, this central moment distribution, although it has a very complex structure, but it must be unimodal-like and with the mode and medium close to 0. And because of that, and as we previously said, the unimodal, for unimodal distribution, it has very nice structure that in most cases it should be ordered, and even if it is not ordered, the inequality should be valid. This inequality should be valid in most cases. And therefore, it is possible why we can use a symmetric weighted average to estimate such a kernel distribution. Yes, because this unimodal structure guarantees in this way. That means, for example, even first it is ordered, so we can use a symmetric weighted average to estimate that, and it will host the mean symmetric weighted average medium inequality. And also, even if it is not ordered, because it is symmetric, as we said that for unimodal distribution, in most cases, the violation of non-ordinals will occur when the distribution is relatively symmetry. So if we use a symmetric weighted average to estimate such distribution, it will even it is the ordinals is not valid. This mean symmetric weighted average medium inequality might be violated, but even in such cases, this violation will be very small because they are all very close to, because the distribution itself is symmetric, so they should be all very close to the center, to the medium, to the mean, right? So and then this guarantees the validity of our approach to use a robust mean estimator to estimate such a kernel function. And another very important structure is that the central moment kernel distribution is location invariant, and we can also prove that although it is pretty complex and I'm not sure here. This location invariant guarantees that it is possible to defining estimators. For example, that means, for example, if we use estimating the medium of the third central moment, and then we're computing the medium standard deviation. Because this is location invariant, so it is possible, for example, not medium, maybe trim standard deviation, but because it is location invariant, we can just like computing the schooners. The schooners is the third central moment over the standard deviation times over with the power 3, and then we can just over with this power with power 3, and then the result will be location invariant because of the location invariant property of this central moment kernel distribution. And also, finally, we need to emphasize that to avoid confusion, because previously Jordi and Lugosi they proposed a kernel distribution computing the medium of all U statistics and from different disjoint blocks, and their approach is that you have many, for example, the 1, 3, 5, 7, and 9. They consider distributed each pair distributed the samples into several different blocks. Yes, for example here or 9, and then computing the U statistics, and then using the U statistics computing each block. For example, each block you pairwise means, and it is 2. And then consider the medium of all these different U statistics. And this approach is obviously very different from our approach, because it will produce two kinds of finite sample bias, and one is from the number of blocks. Yes, and you can see that just 3, the number sample size just 3. But if we consider the pairwise differences, the number will be much larger. And then also another is because the size of if you consider the block, this is also very small, 1, 3, right? Yes, and this will only be not impact if it is the Hodges-Lehmann kernel. And later they consider French mathematician, they consider medium of randomized U statistics, and they overcome the limit of number of blocks, but the second bias and also remain unsolved. So this is the kernel structure we considered, and we propose a way to study to further study very complex the structure of kernel function distributions with very complex kernel function by decomposing, and maybe it can be extended to other kernel functions.